Welcome to The Explainer, where we break down big ideas. Today, we're going to talk about how AI actually learns, and you might be surprised to find out that it's less about thinking and more about a really, really brilliant system of trial and error. I mean, it really does seem like magic, right? How can a computer learn to spot a cat in a picture without ever knowing what a cat is? Well, the secret isn't some kind of magical intelligence. It's actually just an incredibly powerful and perfected feedback loop. So to really wrap our heads around how a neural network learns, we're going to use an analogy. I want you to picture a blindfolded archer. Their job is to hit a bullseye on a target that they absolutely cannot see. Right now, this archer is our neural network, and it knows nothing. Okay, so what does our blindfolded archer do first? They just take a shot. It's a complete guess, right? A totally random shot in the dark. In the world of AI, this is the network's very first crack at solving the problem. In AI terms, we call this first shot the forward pass. It's where the network takes in all the data, like the pixels from an image, and it just pushes it all the way through its layers to spit out its first, completely random guess. So how does it even make that guess? Well, it's all just math. The input data gets multiplied by a bunch of random numbers called weights. Now, you can think of these weights as all the tiny details of our archer's initial setup. Their stance, their aim, how they're holding the bow. It's all completely random at this point. And after all those calculations are done, the network makes its first official prediction. The arrow is loosed, it flies through the air, and it lands right here. The network's guess is 0.73492. Okay, so the arrow has landed. Now imagine a friend is standing by the target, and they can see exactly where it hit. They shout back some feedback. And this is the most important part of the whole process. This is the beginning of the feedback loop that lets the network learn anything at all. So our network guessed about 0.73, but the bullseye, the actual target we were aiming for, was all the way over at 0.05. Oof, that is a huge miss, not even close. So how do we tell the network how wrong it was in a way it can understand? We use something called a loss function. Just think of it as a ruler. It's a formula that measures the exact distance from where the arrow landed to the center of the bullseye. And the goal, always, is to get that distance, that loss, down to 0. Now, here's a really clever trick that's used here. Most loss functions don't just measure the distance, they square it. Why do that? Well, it heavily penalizes the big misses. A tiny error is one thing, but by squaring it, a huge miss becomes a massive problem that the network knows it needs to fix, like right now. So for our archer's very first shot, the total error, the score of how badly it missed, is this number, 0.24908. This single value is the feedback. It's the only clue the network has to figure out what to do next. All right, this is the crucial point. The network has a number that tells it how much it messed up. The next logical question is, why? Which part of that initial random setup was responsible for such a bad shot? It's time to assign some blame. And this, right here, is where the magic happens. The network takes that final error score and starts working backward, layer by layer. It assigns a tiny piece of the blame to every single setting, every single weight that contributed to the miss. It's basically a process of total accountability. This whole process has a famous name, backpropagation. The term was actually coined way back in 1962 by a guy named Frank Rosenblatt. It's really just a fancy algorithm that uses calculus to trace that error all the way back to its source. It uses a mathematical tool called the chain rule to work backward, one step at a time. It asks, okay, how much did the final output contribute to the error? And how much did the calculation before that contribute to that output? And how much did this specific weight, W5, contribute to that? It pinpoints the exact amount of blame for every single part of the process. And, this is a fascinating little piece of AI history. For decades, this whole idea was basically ignored. Researchers thought artificial neurons should work like real neurons, just simple on or off switches. But you can't assign a little bit of blame to something that's just on or off. Progress stalled until they realized they needed smooth, continuous functions to make this whole blame game possible. So what happens next? Once every part of our archer's aim and stance has its own personal share of the blame, well, it's finally time to actually make an adjustment. The network uses this really simple formula to update every single one of its weights. It basically just takes the old weight and nudges it, just a tiny bit, in the opposite direction of the error it caused. So if a weight pushed the guess too high, it gets nudged down. Simple as that. And here you can see it in action. The weight we were looking at, W5, was nudged down from 0.5 to about 0.45. This tiny adjustment, this is the network learning. This is our archer physically shifting their stance ever so slightly based on the feedback. Now, how big of a nudge does it make? That's controlled by a setting called the learning rate, and it's super important. Think of it like the accelerator in your car. If you set it too high, you'll take huge steps and just fly past the target. If you set it too low, it'll take forever to get anywhere. Obviously, one shot and one little adjustment isn't going to make you a master archer. To even get close to the bullseye, our blindfolded archer needs to practice. They need to repeat this powerful feedback loop over and over and over again. And it turns out there are different practice styles. Batch gradient descent is like our archer shooting a whole quiver of arrows, looking at where they all landed, and then making one big, careful adjustment based on the average miss. Stochastic gradient descent, on the other hand, is like adjusting your aim after every single shot. It's way faster, but the feedback can be a lot noisier. But this is the key takeaway. This entire four-step cycle, guess, score the miss, assign the blame, and adjust the aim, this is the fundamental feedback loop of deep learning. This loop gets repeated thousands, sometimes millions of times, with each cycle making a microscopic improvement until that error is practically zero. Which really brings us to the big question, doesn't it? After millions and millions of these tiny calculated adjustments, has our blindfolded archer actually become intelligent? Or have they just become the perfect vessel for the most powerful form of trial and error that we have ever created?